Alright, thanks for watching, and today we would like to prove the root test, which in my opinion is the most powerful convergence test for series. So let's start with a little example to remind you how it works. So figure out if the following series converges or diverges. So the sum from 0 to infinity of n over 3 to the n, does this converge? Well, and what does the root test say? It says, well, consider the sequence an, which is n over 3 to the n, and consider the nth root. So consider the nth root of this, an to the 1 over n, which is, so this is positive, so we can remove the absolute value, and we get n to the 3 to the n, nth root, which is n to the 1 over n, over 3 to the n to the 1 over n, which simplifies nicely to become n to the 1 over n over 3. That's the first thing, and the next step is just to consider the limit of this as n goes to infinity. So the limit as n goes to infinity of an to the 1 over n, well, that's the limit as n goes to infinity of n to the 1 over n over 3. But remember, in a previous video I've shown that n to the 1 over n goes to 1. So in the end, we're left with 1/3. And because that number is less than 1, we can conclude that the series converges. And in fact, it converges absolutely. And in fact, that is the essence of the root test. Namely, take the nth root of this, find the limit. If the limit is less than 1, here 1/3 is less than 1, then the series converges absolutely. If it's bigger than 1, the series diverges. And if it's equal to 1, we cannot conclude anything. Just a couple of tweaks though before I state it. So this number, we call this alpha. So the limit of the nth root of an, we call it alpha, and it all depends whether alpha is less than 1 or greater than 1. Also, in this example, the limit exists, but in general, the limit does not exist, and we have to replace this with what's called the worst possible limit, or the lim sup, because the lim sup always exists. So in general, the root test says if the lim sup of that is less than 1, then the series converges absolutely, and if it's bigger than 1, then it diverges. So now, with those tweaks, and without further ado, we can finally state the root test. So root test, again, let this thing be a series, and let alpha to again be the lim sup of those things, lim sup as n goes to infinity of the nth root of n. Then again, it's by cases. If alpha is less than 1, like in this scenario, then the series converges absolutely. Then the series of an converges absolutely, meaning the absolute value of the series of absolute values converges. And if alpha is bigger than 1, then the series diverges. And if alpha equals 1, then basically you have to look for another test because it's inconclusive. Then the root test is inconclusive. It doesn't mean that it converges or diverges, it's just we don't know. It might converge, it might diverge. You really have to look for another test. to do this. All right, and now let's prove the root test. And the proof is quite neat. So we'll do it, we'll start with 1, and then we'll do 2, and then we'll do 3. So proof of 1. And let me first of all give you the main idea. So the main idea, and then we'll do it more rigorously. Here's the main idea, and it's a bit hand-wavy, but we'll make it rigorous very soon. So the main idea is, if alpha is less than 1, then the worst possible limit of this is less than 1. So in particular for large n, what we get is a to the n. The nth root of an is less than or equal to alpha is less than 1. So really for large n, what we get is an is less than or equal to alpha to the n, which means, again, for large n, the series of a to the n is less than or equal to the series of alpha to the n, but that's just a geometric series with alpha less than 1, so this geometric series converges. And therefore, this series converges, which means that an, the series, converges absolutely. But again, that's very hand-wavy, and this is not necessarily true. That's why we have to do it more rigorously. But again, just to keep in mind what is going on. All right, now, here is the thing. Just like, and in fact, the proof is similar to the proof of the pre-ratio test. So just like the pre-ratio test, we need some wiggle room between alpha and 1. So let epsilon simply be some number such that alpha plus epsilon is between alpha and 1. So let epsilon be such that alpha plus epsilon is less than 1, and of course greater than alpha. But it's this part that's very important, because this will be your geometric series part. And again, we need this because we need a little bit of wiggle room between alpha and 1. And it also explains why for alpha equals 1, this proof doesn't work. Now, remember, we know that the lim sup is alpha. What does it mean to be a lim sup? So, we know that the lim sup, so alpha, which is the lim sup as n goes to infinity of those n roots. So we know the lim sup equals to alpha, but remember, what is the lim sup? It is the sup, but after a very large threshold. So if you have capital N, then the lim sup is just the sup of your sequence after that region. So in other words, what it is the limit as your threshold goes to infinity of the suprema of the sequence after your threshold. Right. So, therefore, what do we get? We get that this limit is actually equal to alpha. Now, what does it mean for something to be a limit? Remember, it's this epsilon n definition. So we know for all epsilon, therefore, for this epsilon, we have the following. So by definition of a limit, we know that there is some threshold. I usually want to write capital N, but we already have capital N here, so let's write capital N1, such that if N is bigger than capital N1, then the difference between our sequence here, which is this whole thing, supremum of an to the 1 over n, where n is bigger than capital N, minus alpha is less than epsilon. Okay, now, here's the thing. Again, this sequence depends on capital N. Okay. Look, if this is true for all capital N after that threshold, it's definitely true for at least one capital N after that threshold. For instance, if everyone in the class passes, then you pass as well. So if it is true for all capital N, it is in particular true for one of the capital N's. So what we can say with confidence now, there is at least one capital N is capital N such that this supremum, the difference between that supremum and alpha is less than epsilon. Again, it is actually true for infinitely many capital N, so in particular it is true for at least one of them. Good. In fact, that's enough. That's all that we need. So now, let's just write this without absolute values. So in particular, what we can say is that the supremum of an of 1 over n, where n is bigger than capital N, minus alpha is less than epsilon. So in particular, this is true, and therefore, that supremum of an to the 1 over capital N, 1 over n, after that threshold, is less than alpha plus epsilon. Okay, but now look, the supremum is like a max. So if I tell you the biggest value is less than alpha plus epsilon, kind of like that, if the supremum is less than alpha plus epsilon, it means for all n, this is less than alpha plus epsilon. So this is for n if you want. So for all n bigger than capital N, we get that alpha an to the 1 over n is less than alpha plus epsilon. But that's perfect. This will give us a geometric series that we want. Therefore, what we obtain, let me put this here. Therefore, we get an is less than alpha plus epsilon to the n, at least for large n. Okay, but then what does that tell us? It tells us that if you take the series of an, at least after capital N, it'll be smaller than this series. So therefore, the sum from n, well, remember we need bigger than capital N, so greater than or equal to capital N plus 1, to infinity of an is less than or equal to the sum from n equals capital N plus 1 to infinity of alpha plus epsilon to the n. But the point is, the latter is a geometric series, because this is just of the form sum n from n plus 1 to infinity of r to the n, where r is just alpha plus epsilon, which, remember, we chose it to be less than 1. Therefore, since this converges, so since this sum converges, by comparison, this sum converges. That this thing converges. But then you you see that was the important part of this series. All the terms for large values of n, but then in particular the whole series converges. Because at the beginning you're just adding a couple of terms. So therefore, hence, this series, so sum, let's say, from 1 to infinity of an, which is a1 plus a2 plus dot 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 plus a capital N plus the other sum from n equals capital N plus 1 to infinity of an converges. And again, that's by comparison test. So and therefore this converges, but what does it mean for that series to converge? It means that an, the series of an, converges absolutely. Alright, and now, so that was the proof of 1. Now let me prove 2. Alright, now let's prove the second part, which simply says that if alpha, so the limb sup, is greater than 1, then the series diverges. And you'll see this part is much, much easier to do than the first part because of the following. So notice, what was alpha? It was the limb sup, as n goes to infinity, of an to the 1 over n. That's alpha. However, remember, limb sup isn't just some abstract concept. There's actually a way to get to that limb sup with a subsequence. Meaning that no matter what the sequence an is, there's always a subsequence of an that converges to the limb sup. Maybe like this. In other words, there's always an express train that leads to limb sup. So from section 11, we know that there is a subsequence let's call it a and k to the 1 over nk that converges to alpha. To alpha, which I like to remind you is bigger than 1. But forget about subsequence for a second. What does it mean for a sequence to converge to something bigger than 1? Well, let's look at the following. So this is 1 and this is alpha. You can rigorously show that, well, if a sequence converges to alpha, then for sure, eventually, it must be bigger than 1. So there's some threshold, let's say capital N, such that after that threshold, your sequence is bigger than 1. Therefore, eventually, so let's say for large k, we actually get that a and k to the 1 over nk, it's bigger than 1, right? And because it's close to alpha. So for sure it's bigger than 1, and therefore, just taking nkth power, we get a and k, it's bigger than 1 to the nk, and therefore a and k is bigger than 1. So what do we get? We have, if you want, the sequence an, and we know that some subsequence is never close to 0. So if this is 0, okay. And then, well, we have the sequence an, but we know the subsequence a and k is always at least 1 away from 0. But the question is, well, can that sequence, the full sequence an, possibly converge to 0? Well, Well, not really, because if an converged to 0, then the subsequence would also converge to 0. So if an converged to 0, then any subsequence, in particular a and k, would converge to 0, which contradicts the fact that a and k is never close to 0, which contradicts the fact that a and k is greater than 1, at least for large k. And therefore, what do we get? We get that an doesn't converge to 0. And therefore, by the divergence test, the series diverges. So by the divergence test, the series of an diverges. And there you go. All right, and last but not least, what about the last fact? What if alpha is 1? How do we show it's inconclusive? Well, let's just find two series with alpha is 1, one which converges and one which diverges. So consider, first of all, the series of 1 over n, from 1 to infinity, then, well, an to the nth root, that's just 1 over n to the nth root, which is 1 over n to the nth root. Well, this, as n goes to infinity, this goes to 1. So alpha equals 1. In that case, alpha equals 1, but this series diverges. So, but this series diverges. On the other hand, consider the 2 series. And now consider this thing 1 over n squared. Well, same thing, an to the 1 over n now becomes 1 over n to the 2 to the n, but you can also show as n goes to infinity, this is 1, but the series converges. Which means if alpha is 1, you cannot conclude anything. It could converge, it could diverge. All right, thank you very much.